Hi folks, welcome to this bonus Saturday video. There were a few requests to do another example of Cramer's rule and determinants of 4x4 matrices. So I'm going to do an example that incorporates both of those things. So in this example, we've been asked to solve for x3. So because we were told to solve for just one variable, that's our clue that Cramer's rule is going to be the approach to take, because we only need to look for one particular variable solution. You could, of course, use inverses or row reduction to solve this, right? You could get it into reduced or echelon form using Gauss-Jordan elimination. And that would be certainly one way to solve, but that would be too much work. It would be, everything. So I'm going to show you two ways to solve this a little bit easier using Cramer's rule. So just a reminder, Cramer's rule says if I want to find x3, I need to find first the determinant of A, that's the coefficient matrix, and then I have to find the determinant of A3. Now, that's the coefficient matrix with the third column replaced by the constant column here. So let's find the determinant of A, and I'm going to find the determinant of A in one way, and then I'm going to find the determinant of A3 in another way, just so you have an idea of what it looks like or feels like to find a 4x4 determinant. So I'm going to start out by writing A. So A is going to be, our columns are going to be 4, 3, 7, 1, 1, 7, 3, 1, 1, negative 1, negative 5, 1, and 1, 1, 8, 2. Okay, so I think I'm going to turn this into an upper triangular matrix. So I'm going to keep the values along the diagonal and above, and I'm going to turn all of these into zeros. So this is really going to be very similar to, our usual Gauss-Jordan or Gaussian elimination, getting these zeros here, but I'm not going to have to incorporate this fifth column, so that saves a little bit of work. And I don't really care if I have ones along the diagonal. I just need to make sure I get zeros in these spots. Now, I am going to start out by switching row 4 and row 1, because there's a 1 here, and that's going to make it easier to do some subtracting, but pretty sure we're going to end up with some big numbers, pretty sure we're going to end up with some fractions for this problem. Oh, golly. So it's okay. Just stepped on a marker cap. We'll survive. So here we go. So we're going to do switching row 1 and 4. So that's going to give me 1, 1, 1, 2. And then 3, 7, negative 1, 1, and 7, 3, negative 5, 8. And then 4, 1, 1, 1. So now to get zeros where I would like them to be, I'm going to subtract an appropriate multiple of row 1 from each of the other 3 rows. So I'm going to do row 2 minus 3 row 1, row 3 minus 7 row 1, and row 4 minus 4 row 1. So row 1 is going to remain the same. We've got 1, 1, 1, 2. 3 minus 3 is 0. 7 minus 3 is 4. Negative 1 minus 3 is a negative 4. And 1 minus 6 is a negative 5. 7 minus 7 is 0. 3 minus 7 is a negative 4. Negative 5 minus 7 is a negative 12. And 8 minus 14 is a negative 6. 4 minus 4 is 0. 1 minus 4 is a negative 3. 1 minus 4 is a negative 3. And 1 minus 8 is a negative 7. Okay, so what I'm going to do next, I'm going to work to get a 1 in this spot by adding this row here. And then I'll be able to use that 1 to get rid of those 2 values, making them zeros. So I'm going to do row 2 plus row 4. So 1, 1, 1, 2. Negative 0. 4 minus 3 is 1. Negative 4 minus 3 is a negative 7. And negative 5 minus 7 is a negative 12. Okay. All right, so now I'm going to do row 3 plus 4 of row 2, and I'm going to do row 4 plus 3 of row 2. So 1, 1, 1, 2, 0, 1, negative 7, negative 12, 0, 0. Now I have negative 12 minus 28, right? Yeah, that's a negative 40. Now I have negative 6 minus 48. It's a negative 54. Then I get 0. Negative 3 plus 3 is 0. Negative 3 minus 21 is a negative 24. And then negative 7 minus 36 is a minus 43. I'm just going to check my arithmetic very quickly because I've been making lots of arithmetical mistakes today. So negative 12 minus 7 times 4, negative 40, negative 6 minus 12 times 4, negative 54, negative 3 minus 7 times 3, and negative 7 minus 12 times 3. Okay, excellent. Less excellent is that we have these less than ideal numbers here to work with, but you know what, that's okay. We only have one more thing to get rid of. So if we end up with fractions at this point, it's not the end of the world. So what I'm gonna do is I'm gonna take row 4 and I'm gonna subtract 24/40ths of row 3. So row 4 minus 24/40ths of row 3. And just a note to myself here, 24/40ths is the same as 3/5. Yeah, because 8 goes into both. Okay. So first 3 rows the same. 1, 1, 1, 2, 0, 1, minus 7, minus 12, 0, 0, minus 40, minus 54, 0, 0. So now when I do a negative 24 minus 40 times a negative 24/40ths, the minus is turned into a plus, the 40s cancel, and I get 24. So 24 and 24 makes 0. That's why I picked that. Now I'm going to do negative 43 minus, this is going to be plus 54 times 24 over 40. So that's essentially what we're doing. I'm just going to go ahead and throw that in here. And that's going to give me a negative 53 over 5. Okay, cool. So now we have a triangular matrix. So what that means is we can find the determinant of this triangular matrix just by multiplying the diagonal entries. So, okay, oh, this isn't going to be too bad because 5 will go into 40. So that's going to get rid of that fraction. So we end up with a whole amount. That's nice. But we can't just do that because we did row operations. We have to think about how the row operations are going to impact our final determinant. So when you switch two rows, as we did in this first step, you're going to have to multiply by a -1 at the end, because that's going to change the sign. All of the other steps I think we did have no impact. So if you add or subtract a multiple of one row from or to another, that's not going to change anything. So we're good. Okay. Yeah, we're good. Now, if I had chosen my last step to multiply this row by 5, at the end, I'd have to divide by 5 as well. So the only impact this is going to have from our row operations is we're going to have to multiply by a -1. So we're going to end up with a negative number. This is going to be an 8. 8 times 3 is 24, 42, and we get a negative. I think that's what I needed to get. All right, -424. So we just found the determinant of A was -424. Okay, now this is a lot of work, these row operations, and they were kind of arithmetically tricky. So we can certainly do this approach, and this approach would have been easier than if we just used the cofactor expansion like usual. If we had done cofactor expansion at the beginning, we would have had to do, like, if I went along the top row, I would have to do 4 times this determinant, and a 3 by 3 determinant has 3 2 by 2 determinants cooked up into it. So this would really be this 4, and then I'd have to find 3 determinants, and then I'd have 1, and then have to find the determinant of another 3 by 3, which would be another 3 determinants, and then again, and then again. So all told, I'd end up with 12 2 by 2 determinants in order to find the determinant of this 4 by 4. We could certainly do that, but it would actually be much longer and challenging than this. So this is one approach that you can take to finding your 4 by 4 determinant if you don't want to use cofactor expansion. You can use row operations to turn it into either a lower or upper triangular matrix, and then you can multiply along the diagonal and then take each of those row operations into consideration. I will mention this is not my favorite method, because we might as well have just added on that last column and solved the whole system from the get-go. But you know, this is certainly one approach to take. So now that we found this determinant, we need to find the determinant of A3. So I'm going to get rid of all of this. And I'm going to show you my preferred method for finding a 4 by 4 determinant. And again, this is just a personal preference, because I like to kind of get away with the least amount of work. And this method seems to be, to me, to be a little bit less work. So determinant of A3 says I'm going to take my coefficient matrix, but now I'm replacing this third column with the B's. So I have the first 2 columns are going to be the same: 4, 3, 7, 1, 1, 7, 3, 1. And now this is different. This is 6, 1, -3, 3, 1, 1, 8, 2. So to find the determinant of this matrix, I'm going to kind of start out similarly in that I'm going to be using row reduction or row operations, but my goal is not going to be to get a triangular matrix. My goal in this case is to get a row or column that has zeros everywhere except for one spot. So if I look at this matrix, I actually have a lot of options. So I could use, because I have a lot of 1s in this problem. So for instance, I could get a 1 here and then zeros elsewhere. I could use this one and get zeros elsewhere. I could use this one and use column operations to get zeros there. So a lot of different ways that we can go about this. I'm going to choose to take this one and get zeros in the rows above it. So I'm going to do row 1 minus 4 row 4. And then I'm going to do row 2 minus 3 row 4. And row 3 minus 7 row 4. Now, if I didn't have 1s, or if I had zeros already in some locations, I might make some different choices, but this is the route I'm going to be taking. So let's see, 4 minus 4 is 0. 1 minus 4 is a -3. 6 minus 12 is a -6. And then we have 1 minus 8. Yeah, it's -7. Then I'm subtracting 3. So 3 minus 3 is 0. 7 minus 3 is 4. 1 minus 9 is a -8. And then 1 minus 6 is a -5. And then to finish, we're going to subtract 7. So 7 minus 7 is 0. 3 minus 7 is a -4. -3 minus 21 is a -24. And then 8 minus 14 is a -6. Okay, so this is it. That's all I'm going to do for my row operations. So I'm going to stop here because if I want to find this determinant now, I'm going to have, if I expand along this first column, I'm going to have 0 times a determinant, but that doesn't matter. So I'm going to get 0 times whatever is 0, 0 times whatever is 0, 0 times whatever is 0. So really, I'm just going to have this 1 times a 3 by 3 determinant. And I don't mind finding 3 by 3 determinants. I don't think they're that tough. So that's the approach I'm going to take for this problem. So to also help me out, I'm going to check here. All I did was I took multiples of row 4 that I added or subtracted from the other rows. So that's going to result in no change happening. And then to make sure I have the signs correct, remember we have to do -1 to the I plus j power. So if you've been working through these a lot, you might have noticed the pattern where this one's going to be positive, and then negative, positive, negative, and then they kind of alternate. So you get this grid of positives and negatives going on. Because you keep getting alternating even and odd exponents here. So really all that we really needed to look at for this one is I'm going to end up with a -1. So I'm going to get a negative times 1. And then I'm going to get rid of this column and this row. So I have -1 times the determinant of -3, 4, -4, -6, -8, -24, -7, -5, and -6. So now I just have to find this 3 by 3 determinant, negate it, and I'll be good to go. So in this case, I'm going to choose to expand along this middle column because it seems to have the larger numbers and I don't want them showing up more than once. So that's what I'm going to do. So to help me out, this is plus. So I have minus, plus, minus. That's going to help me out as I work through this. So minus a negative is going to give me a +6. I have 6 times -24 minus 20. And I have plus, which means I keep the sign as a -8. 18. 7 times 4 is a 28. And then minus a negative is going to turn that into a +24. 15. And then, oh, -7 times 4 is a -28. So this will turn into +28. So there we go. That's what we're going to end up getting for our determinant. And then we have to negate the whole thing at the end. So I'm just going to throw this into my calculator. Okay, and this is going to give me a -848. So that's my determinant of A3, yeah, a -848. So you can see from my perspective, I think this method is much quicker than trying to do either an upper or lower triangular matrix. Because yeah, finding this 3 by 3 is not the absolute worst. If this had been a 5 by 5, what I might try to do is maybe a similar tactic. So I would get my 5 by 5, I would just have one 4 by 4 to find. And then I would probably use some row reduction again to get that 4 by 4 to have either a row or column of zeros, except for one spot. And then I would probably just deal with that 3 by 3 again. So it really just depends on what your preference is. To finish up this problem, we just have to divide. So negative 848 divided by negative 424 is going to give me 2. All of that delightfully wonderful work for 2. So I hope you found this helpful. And so hopefully this helps you kind of figure out how to find 4x4 determinants or larger determinants. We will see you next week for our continuation of regular linear algebra videos. So have a wonderful day. Bye.